We are going to describe an experiment that can be used to determine the coefficient of viscosity using Stokes' law. So of course this is going to be apparatus. We are going to use a very tall jar like that with a very viscous fluid. By that I mean a very thick fluid, and with definitely we are going to get a solid sphere that we are going to use to drop at the top. When you drop that solid sphere at the top, it is supposed to fall through. But now on this very tall jar, we are going to mark off two places. We are going to mark off just any two places along the tall jar where we anticipate that this solid sphere will be dropping through at a terminal velocity. So we mark it M1 and M2, and we take note of that height through between those markings. So the first thing we are going to do is, first of all, we need to know the density of this viscous fluid that we are using. So if we are using engine oil or we are using porridge, we need to know the density that we are using. And after knowing the density of what we are using, of course, like I had earlier said, we are going to mark 2 points along the jar, and we get the height, which in between we have called that height H1. And then thereafter, we get a solid sphere. Now, again, still this solid sphere, we need to know its density and its radius. And after when we know those, we are going to get that solid sphere whose density and radius we know. And then we are going to gently drop it centrally in that viscous fluid. Of course, when you gently drop it there, it is going to drop down into that very tall jar. And as it is dropping down, you take note on when it hits or it passes the mark M1 up to when it reaches mark M2 as it's dropping through that very tall jar. And so when as it's falling through, you probably have a stop clock. So as it is falling through, when it goes just past M1, you start your stop clock. Then as it's moving, it comes and goes past M2, you stop your stop clock, and then you take note of the time that has been taken for this ball or this solid sphere to fall from M1 to M2. And when that happens, you go ahead and find the terminal velocity. Now we know this is finding terminal velocity experimental. You know that velocity is given by distance over time, right? Or you know that speed is given by distance over time. So it's the same. Speed and velocity. Velocity is just a scalar quantity, but these two are more like the same units. So velocity is the same as density. I mean distance over time. Let me call this distance S over time. So it's the same thing here. We are looking at a ball that is falling through this fluid with no acceleration at constant speed, and so that constant speed can be given by the distance divided that by time. So the distance in this case is the H1, and the time is the time you got on the stop clock. So it means that you go ahead and find the velocity, and that is the terminal velocity Vt. So we find it like that, of that ball that has fallen through, and we use that expression to find the terminal velocity. So we shall denote it as V0, or you can call it Vt like we've been doing before. It's going to be given by h, which so happens to be the distance and the time taken for that ball to fall through point M1 to M2. So after doing that, you can go ahead and find the coefficient of viscosity of this fluid. How? So now that we have our terminal velocity viscous subscript t given as h over t, then we can go ahead and calculate the coefficient of viscosity using this expression. This is the coefficient of viscosity of the liquid, the viscous liquid that we are dealing with, and we got this expression we derived this expression in our previous session. So that is how we can go ahead and find the coefficient of viscosity. After calculating the coefficient of viscosity using this expression that we derived in our previous session, we repeat this experiment. How do we repeat it? It means that we have different solid spheres of different radii. Maybe this is radius R1. You get a radius that is of radius R1. you drop it through, you find the terminal velocity by getting your stop clock. As this solid is falling through, you observe when it has just passed M1, you start your stop clock, then it moves, it reaches M2, you stop your stop clock, then you go ahead and find the velocity that was experienced by that ball of radius R1 by quoting this formula that the speed is going to be equal to distance divided by time, the distance in this case being the height, h1, divide that by the time. So you repeat this expression, this same experiment, using another ball of another radius, let's call it R2. Then you do the same. Then you get another ball with a different radius, R3. You do the same procedure, you get another ball of R4, you do the same procedures. In other words, the terminal velocities V subscript T are measured for different solid spheres with different radiuses. So after doing this, then you go ahead and tabulate your results. Of course, as you tabulate your results, you're going to tabulate results with you're going to have a column for the terminal velocity you've been getting. Then you're going to have another column for the radius, the terminal velocity that is corresponding to the different balls of the different radiuses you've been getting. Now in your table of results, you need to include r squared. So you're going to get these r squared and include them in your table right there. And after doing that, you tabulate your values, including values of r squared. Then you go ahead and start doing the math. Now from our previous session, still we derived this expression. We derived the expression that that the terminal velocity can still be given by this expression. And from this expression, you realize that when we were carrying out our experiment, we were getting terminal velocities, and in our table of results we have r squared. Now you realize that Vt and r squared, this is in the form of y is equal to mx plus c, and for those of us who do maths, y is equal to mx plus c is a straight line is a linear form of an equation. This 2 is a constant times this g. G is gravity, gravity is constant, 9 is a constant, coefficient of viscosity of the liquid. We are using the same liquid, so this figure does not change. We have the density of the sphere, we are using the sphere of the same density, the same kind of sphere, so it doesn't change. Then the density of the fluid also doesn't change, we are using the same fluid. From all this, you realize that this expression that is in black is constant, and what is changing according to our experiment, the things that we are varying are the terminal velocity we are getting as a result of using solid spheres of different radii. Since these two are the ones that are changing, realize that all this thing is in the form of y is equal to mx plus c, where y is the same as our terminal velocity and our value of x is our r squared. And this value of m, which so happens to be the gradient, represents this whole expression in the middle. So in other words, if we went ahead and drew a graph of y against x, and we drew a graph, and the graph was such that the gradient of this graph is m. M is the slope. Now, this value of y would stand for Vt, the terminal velocity, and this value of x would stand for r squared. And so if we are to draw a graph, the slope of that graph would be this expression in between, and that is exactly what we do. We draw a graph of Vt, which is in meters per second squared, against r squared, which is in meters squared, and get the slope of that graph, which we shall call slope m. And this slope of the graph is equal to the expressions that are constant in our expression. Our value of m here, this is equivalent to 2g times this expression, which is that, divide that by 9 times the coefficient of viscosity. So that is the slope. Our value of m is equal to this. And now that we have our value of m, and the objective of our experiment here is to find the coefficient of viscosity using Stokes' law. So we make the subject of the formula in our next step, and you realize that we can get the coefficient of viscosity by this expression, with m being the slope of the graph that we attained from our experiment. And this is how we can experimentally determine the coefficient of viscosity of a fluid or a viscous fluid using Stokes' law. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.